All right, now we're going to cover RSA. Okay? All right. Revest, Shamir, Alderman. And if you're reading that book, I think one of you is. It's they cover a whole bunch of it. Yeah, that's right. Sam he's the only one who got the question right. So it's a good book. Y'all just take the time and read the darn thing. Okay?
It's not boring like a textbook. It's actually like a story.
It is, and it's like, ooh, what happens next? And what happens next? It's really good. But it's based on real life. Okay. I think I'm going to require it next year, but it was too late to require it for you guys. So.
I get extra credit, right?
Yeah. If you finish that book, I'll make sure you get extra credit. You get extra credit anyway. You're the only one who got the one on the last test.
Sure.
I will have that book very soon.
And you had to read the end of the book to get that.
Yeah, I was like flipping.
It was right at the very end, the epilogue.
It was close.
So, all right. So, all right, let's go back on to RSA here. 1978. It's based on factoring large numbers. Okay. We talked about in the past 2 to the third and then 2 to the fourth. As we get higher, they get a lot harder to do. That's what this is. It says best factoring algorithms are exponential. Those are like EXP problems. No known weaknesses. So, is there any weaknesses? No. So when you see that question, is there any weaknesses? No. Okay. But there are weaknesses. But it's not with the algorithm. There was a device that was broken, basically, but they manipulated the hardware. So it's not that the algorithm was an issue. It was the way the
hardware.
Right, it was the hardware. Right. Okay. So, no known weaknesses. As long as you choose a very large n, which is p times q, okay, and where or p and q are prime numbers, which we're going to see how all this works. I know a couple of you already looked ahead on this, didn't you? Didn't some of you? I think Matthew did, didn't you? Well,
I had the class.
Oh, that's why. That's why. Okay. Choose the relatively prime to the totient of n. That's what's called the totient. And the totient of n is equal to p minus 1 times q minus 1. We're going to cover all this again. Then D, that's the hardest part to figure out. We're going to look at all that again. Okay? And we have our encryption key, which is a combination of E and N. Our decryption key, which is D and N. Then we encrypt our plain text with E mod N. Then we decrypt our ciphertext with D and then the plain text again. Pretty simple to do. Okay? And you will see where some of the other assignments came into play here in a second. Okay, so let's talk about what this totient is. The totient function is what that symbol is. It's also known as Euler's totient function. They actually talk about it in the book too, but I need to come up with a better explanation of it. But this is all I got for now. It's defined as the number of positive integers less than or equal to n that are relatively prime, in other words, do not contain any factors in common with n, where one is counted as being prime with all of them, also known as a toative. Now, here's an example. There are 8 toatives relatively prime to 24. Now, in the past, I have students tell me, rather than doing the calculation we need to do, or, what we're going to do, by counting the number of relatively prime to it, you come up with a different value. But one thing you need to remember is we are using very small numbers for this, and this is not how it should be used. So it's not correct. Just go through the examples we're using, but in the real world, these numbers are excessively small, and you will not do it exactly the same. Okay? So let's talk about the algorithm itself. So we have the Euler's totient function, the number of the positive integers less than n that are relatively prime to n. Okay? So if p is prime, then the totient of p is equal to p minus 1. Okay? If n is equal to p times q, and p and q are prime, then the totient function is basically p minus 1 times q minus 1. So n is p times q. Got that right? Here. This gets easier. Where's my mouse? Okay. See this right here? N is p times q. Everybody got that? Very easy. If I give you p and q, n is p times q. That's easy enough. The totient of n, which is this funky character, this totient of n, is equal to p minus 1 times q minus 1. That's it. Okay? Easy enough? So n is p times q. The totient of n is p minus 1 times q minus 1. So that's it. Don't think anything more into it than that. Don't sit there and try to count up the number of integers. No, that's how you do it. Okay? So it says for any integer x, if n and x are relatively prime, then the x raised to the totient of the n is approximately equal to 1 mod n. So, and a second here, actually I think this is near the end, but you'll see where that comes into play here in a minute. Okay? All right. You know, let me just get it. You don't need to know this, okay? I'm going to just walk you through it. It's a lot easier to understand when I just walk you through it, okay? Because I know a lot of you are probably like, huh? Okay, let's walk through this. So if I give you P and Q of 3 and 11, and as obviously P times Q says 33. So first, okay? Yeah. If I give you P and Q, you can very easily calculate N. No problems there. Y'all agree? So 3 times 11, 3 times 11 is 33. The totient of N is P minus 1 times Q minus 1. So P, which is 3, becomes P minus 1, which is 2. Q minus 1 would be 10. 2 times 10 is 20. So N and the totient N are very easy to calculate. Y'all agree with that? Yeah. Okay. So now we know P, we know Q, we know N, we know totient of N. Then choose E, which is relatively prime to 20. I will give you E. I will choose it for you. So you don't have to worry about calculating E. So I give you P, I give you Q, I give you E. Those 3. So with P, Q, and E, you can find out N, you can find out totient of N. So far, so good. D is where it gets a little tougher. So now we need to find D such that E times D mod 20 is approximately equal to 1, which in this case is 17. I'm going to show you how to do that. It's going to all come clear here in a minute of all this homework I've been having you do. Okay? So the public key is then E. We know E because I gave you E. We know 33 because that's N. So the public key would be 33 and 3. The private key would be 17. In other words, D and N. Okay? What are we doing with P and Q at this point? Nothing. After we calculate N and the totient, we no longer need P and Q. We can throw them away. Now our plain text, in this case, is a big P, which is not the same as a small p, of that's 7. So for encrypting, we take 7 to the E, or 13. So 7 to 13 mod 33, and comes out to 13. Okay. To decrypt, we take 13. Again, the 13 is what the ciphertext was. 13 raised to D, which is in 17. So 13 to the 17th power, mod n, we get 7. And we're back to where we started from. Everybody see that? Very, very basic math. So with the exception of D, we got this? So if I give you P and Q, you can calculate N. Remember, P times Q. Totient of N is P minus 1 times Q minus 1. I give you E, then it's nothing more than P to the E mod N and C to the D mod N. That's it. Now we got to look into D in a minute. Okay, calculating D. I make it so confusing, but it's actually quite easy. To compute the value for D, use the extended Euclidean algorithm to calculate it. It's also known as modular inversion. Okay? All right. We're going to get to there in a minute. Okay? I don't know why. I need to move the slide forward and make it easier, but I don't. But we will get to D in a minute. Pretend we know D. Okay? So, how do we use RSA? First of all, we choose prime numbers, P and Q, that are 100 digits long. Hence, my little teeny tiny numbers of 3 and 11 are not long enough, and it doesn't work quite right. But it's okay for an example. So we calculate N, which is P times Q. So 200 digits will end up being 512 bits, or so on and so forth. So in other words, we end up with some very large numbers. Do you agree that N will be a very large number? Because if P and Q are both 100 digits each, we're talking some big numbers here. Choose E, large E, and again, we already were talking about a 124-bit number, so a large number to that. Compute D, which we haven't done yet. And then we got our public key and our private key, that's all we need. We can then throw away the rest. Okay? All right, so what the heck is congruent? Because D, you'll notice here, it says, compute D such that E times D is approximately equal to 1 mod totient of N congruent. What it means is corresponding or congruous. It says coincides exactly with superimposed congruent triangles. that's handy. Or basically, or is relative to two numbers that have the same remainder when divided by a third number. For example, 11 and 26 are congruent when the modulus is 5. So you'll end up with the same number. Okay? Is it critical you know that? No. But it's going to be critical in a minute. So here's an example. So if I give you P and Q, 3 and 11, we can do this very easily. Okay? So P and Q, 3 and 11. So N is 33. Totient of N is 20. E is 13. Well, we have to get D. Where do we get D from? All right. Remember this? That whole comparison thing I said you need to know how to do way back when?
Comparison method.
Yes. This is it. But instead, we used N and W, didn't we?
Yeah.
Here we're using the totient of N and E.
But it's the same.
Use the totient of N and E and then do everything else exactly the same. That's how you get D. Okay? So instead of N and W, use totient of N. What's totient of N?
D minus 1.
Not D.
P.
P minus 1
Times Q.
times Q minus 1. So totient of N would be P minus 1 times Q minus 1. And I give you E. So I mean, you've got to figure out one thing, then you just got to do the comparison. And that's how we got 17. Right?
I bet those.
Just be careful. How many of you missed the assignment where the answer was 1? Just one of you? 2 of you? Okay. There's always a few people who miss it. I think I even said it in the lecture. I'm like, make sure you check this top
Yeah, I
one.
completely spaced it. I went all the way down to 4. It's like, oh, okay.
But you got to be careful with this because I tell you, a stupid math error will get you every time.
Yeah.
And hell, I get them all the time too. So that's how you calculate D. Pretty simple to do. Okay. So let me go back one more slide. So now that we know how to get D, this is pretty simple to do. So E times what number of mod 20 was it? That ends up being 17. Okay. All right. So summary: we know N is P times Q, where they're distinct prime numbers. Totient of N is P minus 1 times Q minus 1. Don't worry about calculating E because I will give you E. We know how to do D. D is right there. Do not type that function in the title into Google. You will not get 17. It ain't going to happen.
Google's smart, but not that smart.
Yeah. Well, there's many different ways to do these things is the problem. And, mathematical inversion is still not exactly the same thing. So, all right. So we know how to calculate D. We know how to calculate C. And then, whoa, what's M? Everybody know what M is? Have I mentioned M yet?
No.
Okay, so what on the second bullet from the bottom, where'd it go? Anything look familiar there? C equals 7 to the 13. What's 7? Plain text. So isn't that the same thing there? Just instead of a P, I put an M? It's just a letter. Remember, ciphertext is some value raised to E or encrypted with E, mod N. And then the plain text mod D is mod N. So that's
And for message.
basically, remember, this was our plain text. This was the 7. Then when we decrypted our ciphertext, we ended up with the 7 again. So, same thing. Nothing new there. Okay, I think that's it. Okay? Any questions on RSA? Easy enough? I mean, it's very, very simple. Calculate N, calculate totient of N, D, and the rest is, unless you screw up basic math there. And we all have calculators anyway. Is it going dark out there? Yeah. It's our new wonderful motion sensor lights.
It's the one saving.
All right. That's RSA.